This is another example of the limit definition of our definite integral. So if you remember, we're trying to find this area here under the curve, the negative, and the positive, from 0 to 2. But what we're using are rectangles to get an approximation. So we're going to be doing a right, and so we're going to start by making our partition and then breaking it up into our subintervals. So we're doing 4 subintervals, so that one in the front is a point. And then we're going to do it from the right. So starting at that point, that point, that point, and that point. So this would be our x sub 1, our x sub 2, our x sub 3, and our x sub 4. Those are our points that we're going to be using. And so this one is just 0. And then the bottom one would be our negative. And it should look like this. Just a better picture. So you can see that we have our endpoints here, 0.5, 1, 1.5, and 2 starting at the right. And so our y values will be negative 1.75, 0, 2.25, and 5. But to find those, we're going to take our x sub 1 equals 0.5, our x sub 2 which equals 1, 1.5, and 2, and we're going to plug them in. But first you have to find our delta x. And so that would be our a and b. So 2 take away 0 over n. And our n here is 4. So this is 1/2 or 0.5 like we have. So our area would be our width times our heights. So again, that would be delta x times, and then all of our heights. So we're going to plug in x sub 1, x sub 2, x sub 3, and x sub 4. And they're down here. So let's plug everything in. We get 0.5, and then this would become f of 0.5, f of 1, f of 1.5, and f of 2. So plugging those into our calculator, we end up with our heights, which are negative 0.75, 1.75, 0, 2.25, and 5. So negative 1.75, 0, 2, and then the last one was 5. So checking them again, negative 0.75, 0, 2.25, and 5 are our heights. So 2.25 is what it should have been, and then 5. And so if we multiply all that by 0.5, we will get our answer, which is 2.75. And so now what we're going to do is take this right here, 2.75, and we're going to take the limit as n approaches infinity, and that will fill it in. So that means we're going to get a lot more rectangles, but exactly the same starting setup. We're going to find everything we need and then go off to infinity, and it'll fill it in, giving us an area that's exact. And that's not it. Pretty close, but not quite it. We got to go to infinity. So same thing as before. We went over all of this and what it means. So now change in x, just like before, our delta x. So our b here, let's write our interval. We know we're going from 0 to 2. And our f of x would equal x squared plus 2x minus 3. So we have our f of x, and we have it. So again, this is our height, right? And this is our width. So it works the same way inside. This is our height, and this is our width, dx. So you can see that we're doing the same thing that we've been doing there. It's just summing up the rectangles. So our b here is 2, take away 0, and the n is going off to infinity, so you have to leave it. And then our first point would be from 0 plus I, and then now we can put in our 2 over n. So just like we did up here, our first point was 0, right, plus 1 delta x. So 0 plus 0.5, that's our first point. And then to get the next point, we're going to plug in 2 here. So it would be 0 plus 2 delta x's, and then 0 plus 3 delta x's, and then 0 plus 4 delta x's, right? And that would have been this one, which had 4 points. Those are our 4 points. But we're going to go off to n, so we leave n alone. Simplifying this, we get 2 over ni. Now that we have our delta x, we can plug that in. So this would become, plugging it across, we get x sub I squared plus 2 x sub I minus 3. And then we can plug that in. So it would become 2 over n I squared plus 2 over n I minus 3. And you notice now we are going from 0, so we don't have to use binomial expansion here. We can just go 4 over n squared I squared plus 4 over n I minus 3. Now we have our f of x sub I right here. We have our delta x, so we have our height. We have our width, and so if you're trying to figure out what these are, you don't have to memorize the formula. So what's the area of a rectangle? It's height times width. So this will become the limit as n approaches infinity. That gives us all of our rectangles, right? And you can also think about your delta x becoming 0, right? It's getting really, really, really thin. The sum of all of it, remember we have to put the sum in there from 1 to n, because that's up here. So it's the sum of all of our heights times the width, and then the limit of all of those rectangles as n goes to infinity. So we plug it in now. So our heights, 4 over n squared I squared plus 4 over ni minus 3 times the height. So again, that's the width. So there's the height and there's the width, right? So it's our f of x sub I and our delta x, and we're multiplying them together. So now we distribute just like we did before, and we do basically the exact same steps every single time. So what we did in the last video is what we're going to do again. We're going to distribute that 2 over n, so that's 8 over n squared n cubed I squared. Remember I said that those n's should have one more than the exponent on the I, plus 8 over n squared I, perfect, minus 6 over n. And there we go. Now we just have to do our summation. So this is the limit as n approaches infinity of the sum, and we're going to do the first one. So 8 over n cubed as I approaches I equals 1 to n of I squared plus the 8 over n squared. I'm not going to separate it again. 8 over n squared, the sum of I equals 1 to n of I, minus the sum of I equals 1 to n of 6 over n. Okay, so now we just use our formulas. So the first one is an I squared, so this is the limit as n approaches infinity of 8 over n cubed, and then it would become the I squared one, which is n plus 1, 2n plus 1 over 6, plus 8 over n squared, n plus 1 over 2, minus, and then that one's just a multiply, so we multiply it by the n. Now 8 over 6 would be 4/3. We rewrite the limit as n approaches infinity. And then if you remember, we're going to take that n cubed and give it to each of these. So I'm going to rewrite it just so that we have it in that form. 8 over 2 is 4. And then that would be 6. That's a minus. Okay, so now we can take and distribute the denominator of n. So 4/3. And then again, it's going to be n over plus 1 over 2n over plus 1 over. Like that. And then this is n times n times n. So again, we're giving 1 to u, 1 to u, and 1 to u. So n, 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 n. You have to distribute it in that parenthesis. Okay, next guy. Plus 4. Same thing. Like that. And again, this is n times n. And so 1 goes there, 1 goes there. So n, n, n. And then the minus 6. So now we can simplify. So cancel, 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 cancel. And we end up with the limit as n approaches infinity. And we should really rewrite this. So 4/3. And then this would be 1 plus 1 over n. 2 plus 1 over n. Plus 4. 1 plus 1 over n. Minus 6. And then applying the limit. 0, you go to 0, you go to 0, you go to 0. And we end up with 4/3 times 1 times 2 plus 4 times 1 minus 6. Plugging that in our calculator, and we get 0.6 repeated, or 2/3. So now we should really plug it back in with our calculator and the integral. So if you think about our integral, right there, it says from 0 to 2, x squared plus 2x minus 3 dx. Again, you want to make sure you understand what everything means. So this is f of x. This is our height of our rectangle, right? So it's f of x delta x. That's what we're looking at. And so this is our delta x, and that's our width. So it's the area, and all that gives us is our interval from 0 to 2. So now if we plug that in our calculator, you can see it's the same answer, which means we did everything correctly. So there's our answer, 2/3. So yes, again, it will get quicker in the next section. You're going to love the next section just because you won't have to do this anymore. But again, we're doing this to kind of get through the idea of what's going on is that you have, first, a finite set of rectangles, and you're taking the limit as it approaches infinity, which will fill it in. And so you can see if I keep making this even bigger, there's a lot. You can't even tell anymore. It looks like it's completely filled in, and that is pretty much it. That is our limit. See, it's 0.666. And so if I kept going even closer, giving it more, watch how much better it gets. So see how it's getting more and more. So as I keep adding this, I keep going towards infinity, this is going to get closer and closer and closer. So that is what's going on with each of these problems. You're creating all of your y values here by plugging in the x's. They're giving us our heights. You're multiplying that height by the width. And then this is giving us the sum of all of those rectangles as n approaches infinity. And that is what's giving us our area under the curve. Thank you.